building high-impact networks in Jamaica, reversing climate change. Where are we going to go? It's kind of interesting because these are huge ideas. And this next guy that's coming out is a pretty casual guy. He's got this way about him. It's comforting. And then he starts using really big words, and you get really excited about what he's talking about. He's going to come out and share something with you that could address a bunch of those issues, not just one. And the neat thing about it is, it's not just him. He's working with a tremendous team, and one of those guys is Jack Yang. And so without further ado, to talk about what he and his partner Jack are working on, John Hursh, everybody.
Your presence here today tells me that you're aware of global issues and you're interested in what's being done at the University of Florida to help save the world. Now, if you've got an idea of your own, or you're just here for the free pizza at lunch, come take a seat, take a breath, because I want you to see what I got. In 34 years, the year will be 2050. The Earth will be recovering from the previous decades because of innovators developing solutions. Solutions allowing a planetary population of nearly 10 billion to thrive without choking the Earth of its resources. These innovators will have developed solutions, as you would expect your trusty innovators to do, but not necessarily how you would have expected them to be developed, as you would expect your trusty innovators to do. In the future, we need more efficient solutions, not necessarily novel in production, but novel in approach and design. In order for 2050 to be a year we look forward to optimistically, we need to be anticipating the drastic measures waiting for us on the other end of this 34-year limbo. So where do we start? I started where I found myself applicable. We're going to be facing some drastic measures, including greenhouse gases, freshwater access, food insecurity, and access to clean energy. In the industry, we use heat exchangers because professors stress using process byproducts to the advantages of the companies we work for in the future. These heat exchangers prevent hot water from being directly added to the environment by heating up an earlier part of the process and saving the company money. In our research, we are focused on using algae to solve these problems. Not only does the algae consume carbon dioxide, but it also prevents the wastewater from reaching harmful algae blooms that are being Now, there is a very important part of this. So a lot of the manure that's being produced in the environment is caused by farm animals, primarily cows. Cows poop so much, there's nearly 1.5 pounds of cow poop per person on the planet daily. A lot of this manure ends up in our rivers and streams. Now, a lot of it is treated as fertilizer, but the majority of it results in our water causing an overflow of nutrients, and this results in the harmful algae blooms. These harmful algae blooms are making water almost unusable. From Singapore to New Zealand, California to the Mississippi Delta, all the way up to Canada, algae blooms are in water, making it toxic and killing people. Now, algae is a very broad term for what are basically plant cells. Not all algae is detrimental to health. Some algae is beneficial to health. Spirulina, a food supplement high in protein and iron, is all algae. Researchers are even turning to algae for cancer treatment. It's a very diverse organism that grows rapidly and has a wide variety of application depending on the species. What we're concerned with in our lab is a species that not only consumes carbon dioxide, consumes the wastewater nutrients, but also produces biofuel as a byproduct of simply existing. In our lab, I work under collaborator Dr. Spiros Svoronos and project lead Dr. Pratap Pulamanapalil, alongside doctoral candidates Jack, Yingshu, and Nuyet. It's a very diverse group of people that I'm proud to say I work with on a weekly basis. So hopefully you're processing the gravity of things here. We're talking about preventing manure nutrients from reaching a harmful algae species by feeding a species we have control over first. And not only is it any species, but it's one isolated from Florida waters by UF faculty, and it produces biofuel building blocks. In the future, we're going to need ideas that serve multiple purposes, and here we're addressing clean water, clean energy, and clean air. Look at this. So traditionally, biofuel gets a bad rap because of the amount of space that soybean and similar crops take up to produce biofuel. Here we see that per unit area, microalgae produces nearly 10 times the amount of biofuel as other options, specifically palm oil, the closest competitor. That an order of magnitude. That's insane. How would you like to have 10 times more vacation time in your life, or your grocery bill always being 90% off? Even within the biofuel community, algae is dominating other options in terms of land use efficiency. But wait, there's more. So great, you've got clean air, clean water, and you're producing biofuel on the side. But what do you do with all that algae when it's growing? You can't let it multiply forever. Yes, that's right, save the world. See, the microalgae doesn't need all the nutrients it absorbs. It just stockpiles a lot of it. And let us not forget what we've been using manure for this entire time: fertilizer. In our lab, my amazing colleague Jack, for the purposes of the One World project, has engineered a special bead about the same size and consistency as the tapioca balls you find in your bubble tea. These beads have the algae inside of them, and you can unload them from a bioreactor as easily as you loaded them in the first place. Farmers have it rough as it is, especially a population declining in number and rising in average age. Let's make crop farming a more attractive option, including agricultural farming for dairy farms and other animals. Let's give farmers the option to include biofuel and fertilizer in their annual harvest. By association, we could revolutionize the agricultural industry. In the future, we need our ideas to be all-encompassing. And when we have a solution that serves multiple purposes and addresses multiple problems, we should jump on the opportunity when we come across it. In our lab, we will continue to look forward in finding applications for algae processes, maybe continuing in the dairy farm industry or moving on beyond that. But what about you? I don't stand here any better than you because I'm working on an extraordinary project. I'm in my third year, and it was only this last summer I was emailing professionals in the industry about various articles they'd written on the internet. Only one got back to me, and he mentioned algae, so I looked into it. From there, I emailed every listed algae company in the US, and only a few got back to me about the direction of research. So I went on from there. I found one of my professors, Dr. Spiros Svoronos, and he was a collaborator on an algae project, Dr. Pratap's. From there, I was working there for a couple months, and someone told me I should make an appointment with a very busy guy named Tony. To be extraordinary, you don't have to do extraordinary things. You can try and fail and still be extraordinary. That you try is what makes you extraordinary. Don't forget to try, because all it takes is one.